Okay, so let's start with CNNs, or Convolutional Neural Networks. They are primarily used for image processing by breaking the image into smaller components for analysis, identification, and classification, and subsequent processing, i.e. for motion paths and deeper classification, etc., or generative output as well. They are most often paired with a stimuli neural net, such as interpreting a text prompt, but this can also be any form of computer perception, such as a camera or sensors in a car. You can see these systems in use whenever you see boxes show up around images and pictures or video, such as in facial recognition systems or autonomous driving, social media filters, etc. Of importance to CNNs are things like edge detection and contrast between pixel densities, color, resolution, depth, etc. Think of how we humans see the world. It's a series of contextual things that make up the view or frame of perception. In that perception, or what we call a frame of reference, each thing stands out for various reasons, and we can isolate it because of the difference to other things in that frame of reference, from very small parts of the frame to the entirety of the frame. As humans, we can also discern context. Now, convolution is the application of filters, also called kernels or feature detectors, on input data, or a 3D tensor that represents an image, and we discussed tensors earlier. This helps to identify features or patterns and their relationship to a cognitive context in the input, and the perception, just like we humans do when we see something. This helps identify features and patterns and the relationship to a cognitive context in the input and the whole perception, just like we humans do when we see something. Now, this is important because we need to know the relationship between things within a perceptive frame of reference for analysis, response, interpretation, etc. Basically, the neural net moves a filter across an input feature to calculate the values of weights and feature values at specific points, and then apply matrix multiplication, etc., to create a feature map that is subsequently used to extract patterns, like an edge or a shape. Now, we'll see an example of this in more detail in the lab. Activation functions, sigmoid, rectified linear unit, etc., convert machine data into another representation, such as a probability. Now, we need to talk about feature maps. Feature maps are effectively arrays of values that represent the activation of a filter at a specific spatial position. It's the dot product of the variance between the filter and the actual feature. In very advanced AI designs, spatial can represent more than just a physical location in a space. It can be a dimensional position in a dimensional space, but we talk about that in the Dev bootcamp. You can think of feature maps in a CNN as the convolution output of light-dark values for each pixel in a grid, with many grids making up a frame of reference. Extended, grids are used to detect edges and further an entire shape within a frame of reference, motion paths between the frames of reference, etc. CNNs also use pooling, using neighborhoods of data to max or average the pool values into fewer values. This is done by taking data, such as a 3x3 pixel grid, and representing it as one single value. So we're reducing the dimensions, but maintaining the data, the relevance. This makes the CNN far more efficient than recording each individual pixel and analyzing it. Dropout is common in CNNs, which is randomly dropping out nodes/features from a neural network during training to make it more general via regularization to prevent overfitting. The idea is to make the model consider or learn generalization beyond its training. And I've discussed regularization previously, and will do so more in the upcoming labs. Then it's basically wash, rinse, and repeat over the entire picture or frame of reference. Backpropagation, as we've discussed, is the updating of weights used in a neural network based on the error between a prediction and a goal. And we'll talk about loss functions coming up in a special section on that. A fully connected layer is a neural net layer where the neurons are connected to neurons in the previous layer. So there's a connection point. It's dragging information forward. It is primarily used to classify images, or even now is being used to classify context or generatively produce output, combined images, that are contextually consistent with the stimuli, like combining a bear and a skateboard. So the layers of a CNN are input, convolution, activation, pooling, fully connected, and finally output. So let's take a very brief look at the code of a CNN, and then we'll play with image CNNs in the lab. So in this code for a simple CNN, we can see convolution layers with an activation function, that's RELU, or rectifier linear unit, we briefly touched on. In this CNN, we import Torch, which is a Python library of tensor tools optimized for using GPUs instead of CPUs to accelerate processing. And this is why NVIDIA is so very popular right now. We discussed tensors earlier, but the connection to CNNs is that tensors form a backbone or foundation of AI image processing. But there are other techniques and technology and methods as well which open vast opportunities to enhance speed and reduce resource loads and just basically develop new innovative technologies. This particular code uses tensors and in fact simply pukes out the tensor stats on completion. We'll work on something with an image in the CNN portion of the upcoming labs, so you'll be able to import your own image. Stride and padding are control elements, and you can see pooling with the max pooling function up there. Now don't worry about the code details for now, just focus on the structures of the CNN. So here we have fully connected layers, and we create a Python function in the def section. Flattening is a dimensional reduction technique of moving from a multi-dimensional to a single vector in the previous convolution and pooling layers while retaining key elemental learned relationship weights and values. The flattening convolution and pooling layers output vector is used as input into the fully connected layer. And in the fully connected layer, we again apply activation functions. Then at the bottom, we create an instance of the CNN. And in this case, we'll just import a random tensor as input data and run it through the CNN model we called. At the end, the output is the post-model learned tensor dimensions. Now think of this as taking in an image and producing a visual understanding of that image for a subsequent processing, like turning a wheel in an autonomous car or generating an output like a comprehensive image. This code is not very image related, but you can see the results of a large coded model on facial recognition videos on the internet where a box appears around a face. Now most of you have seen this using social media filters or anywhere the computer detects an image or part thereof, as we previously described. And this is the output of the CNN when I ran it. Note the last line with the dimensions of the tensor. Now again, in the lab, you will use one of your own uploaded images and work on and play with using a different CNN that's got a few more controls on it. Of course, the image at the top of the slide was generated using a CNN and a diffusion generative model, so these neural nets are all around us today. This image is the ultimate goal of a CNN, or the first step on the path to full artificial perception, with visual recognition in flowing stimuli. Now we still have a long way to go to meet deep multimodal human perception, but this is the first step on the path along with natural language processing. So we're adept at artificial vision and hearing, but artificial smell, touch, and taste are still a bit off in the future. Okay, that's enough of the convolutional neural net intro for now. Let's move on to GANs.